Thank you for that introduction, Tim. And it's nice to be here virtually. So as Tim mentioned, I do a lot of different things in my research group. Hardware security is one of the main ones, but I also do a lot of work in hardware design, acceleration, FPGA, and cyber physical systems. So Tim mentioned a little bit about the Engineers for Exploration program. And yeah, maybe if I have a bit of time, I can pull up some slides on that and show you some things there. It's a really cool thing. But since I only have about an hour, I'll keep to security, where I've also been doing a lot of work. In fact, my earliest work in this space was in FPGA security. So even before the gate level information flow tracking. And we did a little bit of work after that on 3D ICs in security for that. So we've been working in this space for quite some time. So today is some kind of old work and some new work. It's a continuation of a lot of the information flow tracking work that I've done over the past decade or more, and how to use that more specifically. I think those information flow tracking tools are pretty mature to the point where we have a company. We are selling those tools to a large number of mostly semiconductor companies. They're using those tools successfully. So the large part of my discussion, my talk today, will be how do we more effectively use those information flow tracking tools, or just generally, how do we more effectively do hardware security? And my hypothesis is that if we can formalize the threat model with some properties, then we're going to have a lot better opportunity to be able to secure our hardware. Oh, something. Oh, there we go. Oh no, give me 1 second. Sorry. There we go. Okay, so I'd like to start off with this question for this talk, and it's a bit of a loaded question, and you'll see why that is. But I want you to think about this and to ask yourself: do you think that hardware is secure and trustworthy? Right. So the hardware that perhaps you have all around you in your phones, your laptops, your sensors, do you think you can depend on that? Right? Is it secure? So let's dive a little bit into this question to try to come up with an answer. If you don't already have a firm answer, which I'm guessing many of you have a firm answer already. So let's look at hardware designs. Look at them in terms of number of transistors, and also, when possible, the number of lines of code or lines of Verilog that these different hardware designs have. So starting at the beginning, in the 70s with this Intel 4004, of course, Verilog wasn't, I don't think, even around back then when they designed this, but this was a stat from someone who recreated this processor, right? And it has about 1,000 lines of Verilog in order to create this very simple microcontroller, not even a processor probably. And then as you continue to go down and increase in complexity and increase in years, of course, we all know that, Moore's law has been trampling on for a while, and depending on who you ask, it may continue or it may stop soon, but regardless, we're at a pretty substantial number of transistors these days, modern. So some 50 billion transistors for some of these monster FPGAs and GPUs and things like that. Don't know how many lines of Verilog there are, but you could probably do sort of the math, quick and dirty math on these things in order to figure out the ratio. All right, so somewhere about a 10 to 20 to 1 ratio of transistors to lines of code. But regardless, it's a lot of lines of code, right? And hardware design is really just a special form of software design. We're writing software for the most part until the very end when we're manufacturing it. We're giving the blueprints. We're writing all of this code to give the blueprints of the chip to the manufacturer in order to manufacture that chip for us. But it's software design, right? And it's hard. It's a lot harder. That's what we call it, hardware, perhaps. But it is in its essence really just software design. So let's look at equivalent lines of code for different types of software applications. And I found this really interesting Google sheet, in fact, that kind of had all of these numbers from different places and saying, here's the approximate lines or exact lines of code in many cases for different types of software. starting from a very simple app that you would have on your phone, so a small number of things, to somewhere around here, where getting more complex, but these are critical systems, right? These are systems that you would hope that would be secure and trustworthy, right? That these are systems that people have spent a good amount of time trying to assess the trustworthiness and security of these. And they have been hacked. Well, I don't know about the space shuttle or the Raptor, but pacemakers have been hacked. Famously, Dick Cheney, one of our former vice presidents, had a lot of heart problems, and he had a pacemaker that did not have a wireless interface because they were afraid, or the hypothesis is, the theory is that they were afraid that he could be hacked externally to get his heart to basically to get the pacemaker to kill him, right? And there have been demonstrations of that being possible. The wireless open interface was pretty much just open on a lot of pacemakers. So if you had the right knowledge about what it is, you could go in and you can wirelessly say, hey, charge the pacemaker, right? And then you can do some very malicious things. Going on, and I think this is right here, where Boeing has had a ton of problems, of course, with this 787 in terms of safety, probably more than security. So we're starting to get to this point where we say these are probably not secure, right? Is Chrome secure? Probably not, right? Everybody uses it, or a lot of people use it. But does it have security flaws? Well, pretty much patches are coming out, fairly often to fix things up. Is Linux, is Microsoft Office, is Facebook, is Google secure? And then I think you can get an answer there. And if you look at the number of lines of code for these things, you'll see that they're equivalent to some of the large hardware designs that we're building today. So I'll ask again, is hardware secure and trustworthy? So let's think a little bit about how many errors that we have as programmers. And these are not malicious errors. These are just errors that we, as we're programming, that we unmaliciously inject into code just because we're humans in some sense. So there have been studies that show that programmers inject somewhere between 15 to 50 defects per 1,000 lines of code. And surprisingly to me, granted, I've not been in industry for many decades, sadly, people only write 10 to 30 lines of code per day. So the cost per line of code is pretty high, $20 to $40 per lines of code. Verification wise, especially in hardware design, and these numbers are for hardware design, not for software. But verification, we spend a large amount of our time doing verification in hardware, somewhere between 70 and I was on a call yesterday with some people from Mentor Graphics, and they even said 80% now of their time is spent by a hardware designer just to verify that the hardware design is functionally correct. So this is not even saying anything about security or trustworthiness, just functional correctness. Does it do as it is specified to do? And then after a level of verification, we can reduce the number of errors to somewhere around 1 defect per 1,000 lines of code. And in some case, this best case is a NASA, the space shuttle, where they did a massive amount of formal verification, formally modeling the system. Depending on what you read on the internet and what you believe, they either removed all of the bugs or they never found a bug, or maybe they found very few, one bug, or perhaps estimating some small number of bugs. But the point is you can reduce the number of errors by performing verification. Right. So if we go back to the previous slide, we're building these massive systems with millions of lines of code, tens of millions of lines of code. We're injecting, as humans, human programmers, we're just injecting some number of lines of code, maybe in the best case, say 1 for thousands of lines of code. So if you go through all of that and you say, well, is our hardware secure and trustworthy? I'm guessing you're leaning to one direction if you weren't already there. And of course, we have a lot of these hardware attacks that have come up in the past, say, 5 years or less. So major attacks, Meltdown and Spectre was one of the biggest ones. And I still remember that time because it was the time at which my parents actually kind of knew what I was doing. And they said, well, this I've heard of this thing, this zombie or this this face off, or they didn't know what the name was, but I heard something about it, and it's in security, hardware security. Is that something related to what you do? And at that point, I knew this was a big deal, right? When my parents can understand, at least to some level, what I'm doing in my research, then that becomes a big deal. So we have these fancy attacks with these fancy logos. You can't have a good hardware attack these days without a fancy logo. And is it secure and trustworthy? And so this is the point. And I say, well, yes, it can be, right? And I'm guessing that most of you were saying no, right? And I think the big point is, what is your threat model, right? And I think the answer for sure, and the answer that you probably all had was no. In the general sense, we cannot be secure and trustworthy, right? Because security and trustworthiness is extremely difficult in the general sense, especially if you have nation state actors with almost unlimited resources. It's going to be a challenge to do anything, to make anything secure. Maybe just don't build the system, and then perhaps it'll be secure. But if, depending on what your threat model is, and this is the key to this talk, it can be secure, right? So this is a really great slide or cartoon by Randall Munroe. I'm guessing most people are familiar with XKCD. If you aren't, please spend some time looking through those. They're great tech humor. It's been going on for a while. But another point sort of demonstrating that security is, or hardware security is on the forefront is, Randall Munroe wrote about this, right? And he wrote this comic, and he said, okay, look, what is, here's the modern tech stack, right? It's not this layers of abstraction. And of course, we have software that abstracts software that abstracts software that eventually hits hardware in your ISA. And then we have abstractions in hardware, RTL, logic level, high level synthesis, physical design, these sort of things. So the joke was, well, we abstract everything in order to make systems work, but we also abstract our threats in some sense, right? And the point where at the top, often our threats are just done by silly things by people, right? People are willing to give out their passwords or not use secure passwords. People are willing to, even NSA people are willing to plug in USB ports that they found in the parking lot, right? They did a study on this where they put some just random USB ports in the parking lot, and some people would plug them into their laptop, even though as government employees, you're not allowed to do that, right? So we have a big threat with just human, right? And that's a hard problem. I don't know how to solve that one. But then you get down and you say, okay, well, look, Randall Munroe is saying that there is some massively exploited hardware vulnerability, and so hardware is here. But if you know anything about XKCD, you have these mouse overs. And so if you mouse over the comic, a little pop-up comes, and here's the pop-up that relates to this. It says, you got to feel bad for these nation state hackers who spent years cultivating some hardware exploit, only to discover that the entire thing that they were looking for was vulnerable by some, in some web browser, right? Some person just didn't design the system and left the port open, right? There are reports of this. There was a Raspberry Pi in NASA that someone installed onto the network, didn't secure it, and people were able to get into the, to the NASA designs, right? Into their software, into their materials. So that, now I'm guessing there are probably people that are trying to hack into NASA as well and making hardware vulnerabilities, but they don't need to do that in some sense, right? They already have this, these people that are willing to, or not willing, but do exploit things at the high level. Okay, so let's talk a little bit about the threat model. And the threat model and properties are sort of synonymous for me, at least. Properties or rules, people call them different things, but are behaviors of the things that you want to defend against, right? So I argue, and I think this is not an argument that is going to be controversial, but I argue that you have to have a threat model in order to make something secure and trustworthy. And if you look at any security paper, you almost always, any good security paper, I should say, has a threat model section, right? Where it says, here's what we care about. And all this other stuff, we're gonna ignore it, right? And why do we do that? Because, as a reviewer, if you don't see that, I can say, oh, what about this? What about this? What did you think about this? And so the threat model is there to say, listen, we know that there's a lot of issues in security, but we only care about these sort of things. And we have to focus on these sort of things in order to make sure that we can do anything, make anything secure. So we talk about things a lot of times in confidentiality, integrity, and availability. So this is the CIA, the triad for security. And here are some things that you might care about. A hardware designer or a low-level, say, firmware system SoC designer might care about in these three areas. So confidentiality relates to information that you want to protect. So these can be secret keys. These can be credit card information, personally identifiable information like your fingerprints or your face ID that the Apple uses to log into your iPhone, those sort of things. So information that should be protected. And a lot of hardware security is spent around protecting those things, making sure that those things do not go to open spaces, to publicly available spaces. Integrity is the dual of that. So integrity basically says I have some untrusted actors in my system, which is extremely common, but I want to make sure that those untrusted actors cannot affect my critical resources in some way, right? So if I'm hardware root of trust, for instance, should not be affected by some app, right? And so you want to make sure that the integrity of your hardware root of trust or the integrity of your boot up process is secure. And then availability has to do with resources or things being available, being there when you need them. So you don't have denial of service attacks, or you can't be locked out temporarily of certain types of things that you may need. So for instance, in cyber physical systems, a lot of times this may be sensor readings or writing to actuators. And often you need to do those in a certain amount of time, right? And this is very closely related to real time. And I add this in as a separate sort of category of threat modeling, specifically for hardware. And I do this because we can, with this information flow tracking, we found that it's possible to do to model timing behaviors at hardware, right? And so we can determine things like, will something happen in a certain amount of time? Will a resource be shared properly? Will I be able to get access to that resource within when I'm supposed to get access to it? Things like that. Right? Can I get my results in a certain amount of time? So all of this has its basis on a pretty substantial person. So Alan Turing, way back when Alan was alive, was saying, how do we check a routine, right, to make sure that it is correct? And so what Turing in his sort of almost infinite wisdom said that, what you need to do is you need to make these assertions, right? So you should have these assertions that sort of say this sort of thing should be happening, right? Or this should happen, or maybe this should not happen, right? And we write these a lot. If you're a good coder, you write these assertions a lot, making sure that bounds are correct and things like that, right? And that, I think, is your hope at making something secure and trustworthy, is that you can build up enough of these assertions that you have enough confidence that your hardware or your system will be secure. So this also follows a lot of sort of hardware work in the functional verification space. Test-driven development. So the idea of you write tests that your system should be adhered to, or your modules should adhere to. And then as you develop your modules, you develop your hardware, you continually test them and you make sure that they're working, maybe add more test scenarios to them, right? So formalizing the properties, which formalizes your threat model and then allows you to design your system in such a way that you can be sure that you are, or have some assurances that you are adhering to your threat model or your security, things that you care about. And then security verifications, again, coming from more of a kind of functional verification space, but this properties first paper is one of many that is related to what I'm advocating here in hardware, but saying that you have these properties at a high level. You specify these properties as soon as you can, as soon as you're developing, as soon as you're articulating what the system should be, what your hardware should be, and then you refine these properties ideally automatically, but even manually is fine as you develop and add more detail to your system. So I'm going to make a comparison to functional verification because I think it's an important one, and argue that that you also need a separate path for security verification. And note how similar these things can and should be. We have spent a huge amount of time trying to do functional verification. And so to ignore all of that work when we want to do security verification is a big mistake, in my opinion. So if you look at the functional verification, typically what you do is you come up with a plan as early as possible. Even when you're just formalizing what the system should be, you should be having a plan for how are you going to verify the different parts of these systems. You have test benches or properties, things that you check, that you can check your design against. And then you have analysis. So when things break, which they inevitably do, you have ways to fix them, understand what's wrong, and figure out how to fix them. So if we look, and try to model this tried and true path of functional verification. So the equivalent in security verification at the beginning is you want to, you have in functional, you have here's what it should do. It should be a crypto core. What does a crypto core do? Well, here are the things that it does, right? Well, same thing for security. You should have, okay, well, here are the things that the crypto core should and should not do, right? It should not leak your key except out of the ciphertext, right? There should not be any side channel, perhaps, right? Things like that you care about. Then you come up with a plan. In this case, you write properties, you think of ways that you can verify these properties. Hopefully you use some tools to do this. But honestly, typically speaking, a lot of companies are just doing this sort of through red teaming. Looking at designs and arguing, asking the designers, hey, did you think about this thing? How did you handle cache side channels? How did you handle power DPA, things like that? And they kind of PowerPoint and whiteboard things, and they say, well, we did this technique, and we talked to Rambus, and they gave us this, and blah 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 blah. But ideally, we can do that in a more sort of formal manner. We create our security test benches, which to this point have largely just been the same as our functional test benches. We haven't seen the need yet to make any security specific test benches, just because I think functional test benches do a really good job of creating a lot of coverage. And then we need some sort of analysis. And this certainly, whole thing is very, very much less mature than, of course, the functional verification. So let me dig this into a little bit more, and then I'll get into some of the work that we've done. So this is the level, or a very kind of abstract, if you will, view of levels of abstractions in hardware design. So we started at the low level, and then we added tools, to make things easier. Right? We started at the beginning with just drawing out stick diagrams of transistors. And we said, this is hard, and we're getting so many transistors. I need some way of automating this. So we developed layout tools at the physical level. This is becoming more challenging. So can we automate this? Yes, we can. And it goes up to logic synthesis and high level synthesis, and even higher up now, electronic system design, things like that we're doing. In functional verification, basically what we do is we do equivalence checks. We say, does this thing that I synthesized, is it still the same as what I expected, what the input was, right? And we have formal ways. Verilog is a formal way of describing the functionality, Verilog and VHDL, system Verilog. So on the other side, we should have these things, right? So we should have these similar types of security tools that plug in at each of these levels to tell us different types of things. So we have our properties, and ideally those properties are refined as we go down the step. And I'll give an example of this in a second. So here is the property-driven flow. We take our designs over here, we take our properties, and then ideally we give those to some design tools, and we do some verification. And I'll show you some aspects of that, but first focusing on a key problem of how do we specify these security properties. And please feel free to ask any questions at any time. I don't see any questions up there, but please ask questions. So how do we do this? And I think, again, sort of rely or looking at how we're doing verification, functional verification, one thing that is used a lot in industry in the functional verification space is verification IP, or VIP. So what are these verification IPs? These are essentially test benches and testing strategies, verification strategies for seeing if your design is correct. And these typically revolve around your interfaces. So your AXI, did you implement AXI correctly? Is something weird happening? Are you not handling some transactions? Is PCIe working correctly to your, right? So they have standard ways and test benches of testing that. And then you plug in your module that is supposed to talk that language. And it'll see if it actually works. And I think we need to do the same thing in security, because I think it's a big challenge to write security properties in general, or just writing formal properties in general is a challenging thing. If anybody knows anything about formal verification, you know that it's hard. At least I think it's hard. And you know that there aren't many people that do formal verification because I think it's challenging, right? It's a hard thing to do. So if we're relying on everybody to become formal experts in specifying these properties, then we're going to have some challenges. So how do we standardize these things? So there's some great efforts going on, mostly, or I think almost all in industry. This common weakness enumeration has been around forever from MITRE. They've focused on software forever, and recently they've started doing hardware design. So they've been adding in some weaknesses and potential vulnerabilities related to hardware designs. And there's a large number of them, and I encourage you to go look at those if you haven't. They're basically these sort of things can happen, right? They give you notions of what you may want to, out of memory, out of bounds, things can happen. We've seen cases where the information leaks to your debug through your JTAG. That's a weakness. You probably should think about that when you're designing a system. Think about whether you care about it. They're not properties per se. They're not formalized. They're still very English language type of things. This shouldn't happen, or this shouldn't happen usually. This is a weakness. Think about this kind of thing. But they're helping lead to people kind of categorize. There's categorization of these properties, but also allowing people then to come in and be like, okay, I can write properties related to CWE 1198, and that will allow me then to have a common language almost. So let me get into some of these notions and go through some examples. And I call these templates. So writing security templates. So the idea is that you can write example properties that then can be sort of plugged into other systems. And I'll start with a SoC firewall. So this is access control. They often call it firewalls in industry, just because I think access control is understating what the problem is. But the idea is that you have all of these different IP cores, tens to hundreds of these, communicating through some on-chip network, some NOC, or something that's AXI related. Anyway, somehow communicating. And a lot of these cores can access things only in certain ways, right? So they have access control policies. The crypto core can only access SRAM, or this portions of SRAM. DSP core cannot access crypto core. CPU can access everything except when it's in debug mode, or when it's in debug mode, but can't access anything, when it's out of debug mode, things like that. So if you want to write some properties or some templates for this, and these are very much similar to sort of what CWEs are. If you look at the MITRE page, one thing you might say is the property is the English language property, or the German language property, perhaps, if you want to translate this, is a hardware core cannot write to an out of range address. And then this is the formalization of this, right? This is a formalization of that property, specifically for AXI, right? And we're developing a bunch of these properties. Yeah, I have the citation there. That's still we haven't released that publicly, but I'm happy to share that with you if anybody's interested. But it's basically saying that here is some way of doing this, and you can, in fact, sort of name your sources and destinations differently. And you reuse this property. So trying to make this into a template, I think, is a good idea. But this is a formalization. This is a property that you can take with the Tortuga tools and verify on the design that it is correct. Other properties, for instance, if you have an illegal access, you might want to send an interrupt, right? So and an interrupt to the root of trust, right? Or if you have so many illegal accesses, 50 illegal accesses within the past few seconds, then send an interrupt, something like that. So more properties, right? And if you look at these properties, they're a little bit different. So if this property had this this funny little thing, if anybody's familiar with system Verilog assertions, you don't see these things, this sort of funny thing. But if you look at this property, this is basically what you would normally see for functional verification. And this is a functional property, right? It's basically just saying that when there is an access that is outside my range, make sure that the interrupt line goes high, right? Now you see that this one is basically saying something a little bit more complicated. It's saying, oh, sorry, no, this is the same thing. So the same thing, there's no flow here. Basically just saying, again, if there's some issue, make sure the interrupt is risen, right? And these are just normal properties. I can write these properties. I can use Cadence, Mentor, Synopsys, whatever your favorite verification tools are, and I can verify that the security of these properties exist. But I can't do it for these with normal tools, right? This does not flow, or this notion of information flowing is extremely difficult, if not impossible, in normal system Verilog assertion properties. So going on, writing some other more generic kind of templates, right? You can have these sort of things where you say, okay, make sure that grant is given to only one core, right? Make sure that grants are given to at most so many cores, right? So some generic things with related properties, and these are system Verilog assertions. Until you get to these things here. These things at the bottom are non-interference. So basically, non-interference is an old security notion that says if I have some things that I say don't trust, those untrusted things, regardless of what they do, should not interfere with the things that I do trust, right? So the idea there is that regardless of what those untrusted things are doing, the execution path, the system state of those trusted things remains the same. And if that's the case, then there's non-interference. So it's a really important property for security, and something that information flow tracking they're very tightly intertwined. And these non-interference properties are things called hyperproperties. So basically they're sets of traces as opposed to sets of traces. So the top ones, the normal properties, what I call functional properties, are defined on sets of traces. Hyperproperties are defined on sets of traces. Fred Schneider at Cornell has done some really amazing work on formalizing all of these notions, but they're harder, basically. They're more difficult. So let me give you a look at some of these properties in the real world. So this is courtesy of my colleagues at Tortuga. So they've been working with Synopsys on their ARC processor. So their ARC processor is essentially just a microprocessor with trust zone in it. So with Synopsys trust zone, I forget what they call it. Secure shield, there it is. And basically you just want to isolate resources. That's what trust zone and these sort of things are doing. You want to say, I want to be able to make sure that things are isolated. If I'm writing some code, that it's isolated. If I put something in this memory space, it's isolated from something else. And so one of the big things that that is here, that is related to kind of the access control thing that I just showed you, is separating out memory. So typically what you have is you have some part of memory that is secure, some part that is non-secure, and what you want to prove that it's never the case where anything secure, any information about things that are that's the data that's in that secure memory could ever go to non-secure memory, right? So in any manner, right? So leakage in any sort of manner, non-interference, right? There's no way that regardless of what I do in that secure thing, the non-secure thing doesn't change. So I could twiddle my bits to my heart's content. I can write and read from secure memory, and regardless of what I do there, the non-secure part operates the same. That is the notion of non-interference, and that's what information flow tracking is giving you the value to say that. So this property is a little bit more complex. That's basically saying this data out, right? This data out should not flow here to data in, right? Should not flow to data in. So a temporal condition, when the addresses are within these ranges, right? So it's okay if the addresses are outside of these ranges for their flow to be from data out to data in, right? But as soon as it's within those ranges, then it's possible, right? So that's the notion there. And the Tortuga language sort of has a few simple decorators, I would say, on it, like these win keywords that allow you to essentially add temporal conditions to your properties, which is extremely important in many cases. So we can handle Trojans. So we have a paper on that. I'm not honestly a huge fan of Trojans. Hopefully not. I think Trojans are important, but I think they've been sort of overworked. But we can do something in Trojans if you really care about that kind of stuff, and some people do for sure. And so this is sort of demonstrating the refinement of the property. So in this case, what you would do is you would assert that the key should only flow, and this is a made-up operator that I did, should only flow to the cipher, nowhere else, right? And then basically you can refine that property as you go down the stack to say, okay, now key should not flow to all outputs ignoring the cipher. And so that's a real property that you can use with Tortuga logic. And then what actually is happening and what the value of Tortuga logic is it's giving you the ability to set labels and track those labels, right? And that's what information flow tracking does, is it gives you the ability to track those. So Tortuga has taken the stance, which is I think a good stance of abstracting away these labels from you. You shouldn't need to worry about these labels. That's a very low level thing that you need to understand what information flow tracking is all about. But let's not worry about that. And let's just write these properties. Right? Another one is a cache timing channel, right? So this is an important one these days with Spectre and Meltdown kinds of things. So here you would say things like, at the high level, I don't want there to be a timing flow, right? So you would have perhaps a new operator. I don't want there to be a flow when they're through the timing channel, right? So there's no functional flow here, right? In cache side channels, it's a timing flow. You're getting the data correctly, but you're just getting the data a little bit sooner or later, depending on what someone else did to the system, right? And that time in which you get the data tells you something about what other people are doing with the system, and is extremely powerful, as people have shown time and time again. You can just extract almost anything about the system through this. You can force the system to use the cache. That's super easy. Force to use the cache in certain ways, and then based upon the state of the cache, you can understand what happened or what the other parts of the system were doing, right? So you can refine that down to flow properties, refine that down to labels, and then perhaps even and this is just almost, I wouldn't say a dream, but this isn't a reality in some sense, but you could say some things like, statistically speaking, I want there to be very little information flow, right? So more of a statistical nature, which there is not a lot of work on, and I think there needs to be a lot more research on more of these statistical properties. So going into this example a little bit further, so I give this cache. I have a cache, and my goal here as a designer is to design a secure cache. I start out with my cache, and here's the properties that I want. I run it through these security tools, and it fails. Not too surprising. It's a cache. We know that it has flaws. So the next thing that I do is I say, okay, let's do the simple thing, and let's just divide the cache into two parts, a secure and a non-secure part. Physically divide them in some sense. Implement this thing, right? Same properties, different design. Run it through this situation, and it will pass if you design it correctly. Great. Well, that's not ideal, right? That's basically limiting the performance of my cache. It's limiting the amount of cache lines that I can use. I'm dividing my sets into two parts, so I'm getting effectively half the number of sets. So I'm not getting as many the ability to store as much data into my cache. So can I do something smarter? There's some brilliant people, Ruby Lee at Princeton that more than a decade ago came out and said, okay, let's think of better ways to do this. Let's do this notion of locking cache lines. So if I have a sensitive information and it goes into a cache line, I'm just going to lock that cache line and make sure that that no one else can use it, right? And that seems like a reasonable thing. So if you don't lock all the cache lines, then you're going to get some decent performance. And then it should be the case where that when you do lock the cache line, there should be no information flow. Okay, so we did this. We actually designed this system ourselves as a sort of proof of concept to use the tools. We wrote the properties, same properties. We ran it through our internal verification tools, so our UCSD non-industrial strength verification tools, and it failed, and we were surprised. And I told my student, Armida, you're probably wrong. You probably designed it wrong. Go back and look at some things and figure out what's going on, right? And she comes back and she says, actually, I'm not wrong. There was a flaw in the PLCache. And this is something that others have recently found as well. So I think Jakob Zeffer has done some great work. He's at Yale now, I believe, on cache timing channels and quantifying it and creating just really some great sort of research on discussing the relationships between all of these things. But if you look at the trace that's output of this, it looks something like this. This is scary, admittedly, but it's basically saying that this is what you're going to get out of these verification tools. You're going to get a trace that says, here is when the flow happens, right? And the flow happens, it can actually change the time at which a result is delivered, right? And I don't have time to go deeply into this, and I don't think it's sort of the focus of my talk, but it's a metadata flow. And what they decided to do in PLCache, which I think was a good decision performance-wise, is that they decided to change the LRU policy. So if you go in and you have a hit, they're going to update the LRU bits, even in locked cache lines, to make sure that you don't get pushed out, right? So it's basically a performance optimization that they didn't think would cause a security flaw. But it ends up, because you're messing around with your LRU, or because they're changing the LRU bits, that you can go in and do things, and you're not changing the functional state of the cache, but you're changing the LRU bits of the cache, and it will cause a timing side channel. Right. And again, I don't want to go through this. I think it's kind of tangential to what I want to say today. But we found this side channel, what that we thought would be in a secure design. Right. This is a paper that has, I don't know, hundreds of citations. It's by one of the probably for certain the leaders in the hardware security field. Ruby has been working in this space for a while. She's industrial experience at HP, and so you would imagine that she would be someone that would understand these things. But the point is that there was a flaw here, right? And was it a flaw that they cared about? Was it in their threat model? Well, that's arguable, right? Is a metadata, cache metadata, is that in the threat model? Probably should be, but there is a flaw regardless, right? And that's what these tools give you. So pushing into kind of the big challenge, a big challenge here is debugging, right? So I get this flaw, and this happens a lot. Happens almost all the time, in fact, is that you write these properties, you put your design through it, and almost always they find something for you. Almost always we found that they find a case where something bad can potentially happen. And then it's up to you as a designer to go back and basically say, how do I fix it, right? This fails. And then I'm in a world of pain now as a designer to try to fix this bug, because it's not a functional bug, right? It's a security bug. It may likely is still functionally correct. I just designed the function incorrectly, insecurely, right? So what happens? Well, we write these properties, great, they fail. Like I said, this almost always happens. And then we go to fix the security flaw. And then the security experts are like, I just wrote these properties. I have no idea how to fix this hardware design. That's up to you, hardware designer, to fix these flaws. I wrote these properties for you. I told you what's important, fix it. The hardware designer is like, I don't understand security. What are you talking about? I'm here just to write gates and transistors and RTO, right? So it's a big challenge, I would say. It's such a big challenge, I decided to do that twice. Okay, so what are the issues here? Some very fundamental problems that we are starting to think about, or just starting to think about, and very open to collaborations if anybody is interested in this. So one of the big problems is, where is your error? So these traces will often go through a large part of your design, but where does the actual vulnerability occur, right? It'll flow through a bunch of things and actually get to some point where it becomes, this is a bad thing. But it's often the case you could sort of stop it early. So when do you stop it, or when are the most important things that you can do? So this is localization, right? Error localization. And there's a decent amount of work in this space for functional verification, but not a whole lot for security verification that I'm aware So we have some drafts basically on this, some work with Yanjing Li and her students at University of Chicago around this work. And the next part is program repair. And so if you can figure out which part of your designs are wrong, can you automatically fix that? And that's something I want to kind of dive into a little bit more, and then I'll kind of wrap up after this. So we have some recent work called VeriSketch, and this is in the program towards program repair, I should say. So what VeriSketch does is that it allows you to basically fill out your design. And it's using this notion of sketching, which is a very popular thing nowadays in software world. And so what sketching in general says is that you can kind of add question marks into your design, right? You say, I don't really know what this variable should be, but can you figure it out? Can you, formal tool, figure it out for me? Can you figure out what this variable should be, given some constraints? And often these constraints are functional constraints. So it should be functionally like this. Here's some functional model of what it should be. And I don't know what the bounds should be, is a typical thing. I don't know what my for loop bound should be. Just put some question marks. I is less than question mark, right? Then figure that out for me to make sure that I don't do a memory out of bounds error or things like that, right? So we brought this into the hardware space. And the notion here is that you can write some modules that maybe won't have any security issues. And then you have some other modules, usually your control logic, that you know that will likely induce some security issues. And you just say, I don't know what they are. They're bubbles, right? And I'm going to write properties. And I want you to create a design. I want you to sketch. I want you to fill in that design for me such that it adheres to those properties. So find me a solution, a valid solution to these question marks in my design, these unknown parts of my design, such that they adhere to my security properties. All right. So how this works is we instrument it. So we use information flow tracking logic. We're using a register transfer level information tracking logic, just because that's our sort of latest and greatest, but it could use any sort of information flow tracking logic. We use a thing called counter example guided inductive synthesis, CGIS, which is a common technique in sketching, basically to iterate between something called verification and synthesis. So it smartly solves a really hard problem by essentially guessing at what the design, filling in a guess with what the question marks in my hardware design should be, then asking, does this design, this filled in design, does it meet my security properties? Likely no. It takes that counter example and then it uses that to guide the next guess, and then it iterates on this process. So it's sort of independently fills in your functionality, checks the security part of it to see if it matches. If it does, great, you pass. If it doesn't, it has this counter example, and then you use that counter example in the next time and to say, I should not be selecting these sort of things because my counter example gave me an indication that they would be wrong, right? And so it's a very complex kind of thing, but it works. So I see a question. So is VeriSketch open source, or do we plan to publish it? It is not, and it's not because it's in bad shape, to be honest. In some sense, I'm not worried about sharing it, but I think sharing it to this point would be giving it to someone and giving you a world of pain to try to figure out what it is. And the student has Armida has graduated and gone on to do security verification at Apple, and so she's probably less interested in helping you out. So yeah, that is sort of the sad truth of that. But hopefully someone will come along and pick it up, and we can open source it. That would be amazing. So some sketching types of things, constructs here. Common things. So I don't know what the constant is. I have a mux, basically. I want to select between some number of operations, right? I want to select between some number of variables. I want to select some value that may be in the past. Or I have some combinational input, right? I don't know what the circuit should be, but I'm going to basically make it into a BDD, and I'm going to fill in that BDD, right? So I'm going to let the sketcher fill in that BDD. Or I have some finite state machine, right? And I don't know what that finite state machine is, but it has this many states and this many transitions. Fill in the states for me. Or maybe I just partially sketch that out. I don't know some of the states, and I add them in there. And I don't know some of the transitions, and I add them. So those are the kinds of things that you can do. So going to that PL sketch. So the hard thing for the PL, the partition lock Ruby Lee work, is this skip thing. So that's what the thing that they messed around with. And the skip thing basically says don't do an access to the cache. Skip the access to the cache, directly go to memory, and don't mess around with the cache, right? So basically just go to memory, get your data, but don't put it in the cache because you're not allowed to do that. That partition is locked, right? And so we can say, well, I don't know what that skip signal is. That's kind of a hard signal for me to figure out, but I know it's a function of these things, of the request, the write request, the hit, the LRU lines, and so on and so forth. And I don't know when I should update my LRU, but I know that's giving me a problem, right? Because I saw it in my trace. So let's update it, based on some function of lock and skip. And you can refine this. So you can make this a little bit more, basically you're saying here, I know that this skip should happen when it's not a hit and some other conditions, but I don't know what the other conditions are. Fill those in for me, create a logical formula for me that decides these for me. And I know that this should be lock is equal to something, right? It's not a function of lock and skip, it's just a function of lock, and I know it should be equal to something. And then at the end of the day, wow, I am getting really bright, huh? It's like I'm coming down from the heavens. I didn't realize my there we go. Should be a little better. Sort of. Okay, now it's only like the Star of David. So it's almost Christmas time, so you can kind of see. At the end of the day, the sketcher will fill it in, right? So this is a correct solution that adheres to those properties, that doesn't have that cache side channel. So we've done this with that example. We've also done it with these firewalls. So many different, so basically we're sketching this FSM internally. And so when do you grant access? And we have a bunch of different conditions that allow you to grant these accesses. We do things in terms of non-interference, you can see. So these should not have flow. So these are a little bit more complicated than just granting access. And the VeriSketch can handle these things. Granted, it can only handle very small things at this point. Okay. So I'm almost out of time, so I'll conclude here. But I'm happy to kind of answer more questions or dig into any details of all this. There's a lot here. In fact, I just gave a 2.5-hour tutorial on all this stuff at Host on Monday. So if you're interested in learning a lot more, and you can probably still register for those tutorials. It was like $50 to get access to 6 tutorials. So it's probably a good deal if you're wanting to learn more about that. But the whole notion of what I discussed today was this idea of property-driven security, hardware security in particular. So the idea that you should write things at the high level. So properties, security properties. You should specify your threat model. You need to specify your threat model as soon as possible. And all of the good companies that are doing, developing secure systems, I'd say, are doing that already. But they're doing it some formally, a lot more just sort of informally in English language or in natural language, saying, here's what I care about, specify those properties, and then ideally have ways and tools, which we're just starting to have these tools, but have these tools that can help automate this verification of these different properties. And if we can do this, then we can get towards having some confidence that your hardware is secure, right? So having a bit more confidence that the thing that you design is secure. And so we have a lot of work that some of I've talked a little, at a very high level that is pushing towards this space. But I think there's a lot more to be done, especially like I said, in using these tools or using information flow tracking tools. There's I think a lot of research that needs to be done there. So with that, I'll conclude.